Thank you, sir. Namaskar and a very good afternoon to one and all from CSIR NEIST Jorhat, India. On behalf of the entire IVWGST 2022 organizing committee, I take this opportunity to welcome the entire online confluence attending this event to day 11, which is also the final day of the third international virtual workshop on global seismology and tectonics. As we all know that today is the ultimate day of this phenomenal virtual workshop. I'm profoundly grateful to each one of you for your constant support and presence during every lecture session of this virtual workshop. On the last day of this event, I'm brimmed with extreme delight and satisfaction at the success, impact, and widespread response that IVWGST has garnered from global audience since its inception in the year 2020. I also take this opportunity to appreciate and extend my gratitude to all of the honorable keynote speakers as well as every single participant for registering with us and showing an overwhelming response to this virtual workshop. On this occasion, I'd like to restate that IVWGST 2022 has been a delightful journey of learning, knowledge sharing, and amalgamation of some of the brilliant minds of the world into a single unified platform. To commemorate the final day of IVWGST 2022, we have arranged a very short valedictory function. Now, may I welcome the honorable dignitaries to the digital dais, please. Honorable Chairperson, Dr. G. Narahari Shastri, Director of CSIR NEF Honor, Dr. V.M. Tiwari, Honorable Director of NGRI, Hyderabad, Dr. Kalachan Sain, Honorable Director of Wadia Institute of Himalayan Geology, Dehradun, Dr. Sukanda Roy, Honorable Director of Borehole Geophysics Resources Limited, Government of India, Dr. Sumer Chopra, Officiating Director General and Director of Institute of Seismological Research, Gandhinagar, Gujarat. Special guest Professor J.R. Kayal, former Deputy Director General, GSI, Government of India. Professor Sagarika Mukhopadhyay, Professor, Indian Institute of Technology, Roorkee. Dr. Vivit Suryanto from Gajah Mada University, Indonesia. Dr. Debojit Hazarika from Wadia Institute of Himalayan Geology. The keynote speaker for final session, Dr. Julian J. Bommer from Imperial College, London. I'd also like to take the opportunity to say that we will be fortunate and glad to have your valuable comments and suggestions regarding the subsequent installation of this workshop. And it would also be great to hear from you regarding the platform to be adopted, that is online, offline, or hybrid mode. Before listening to all the dignitaries on the digital dais, I would like to request two of the participants to experiences of IVWGST 2022. It would be really wonderful to hear from you. But before that, we would be glad to listen to the speeches of all our honorable dignitaries. So now, may I request our honorable director, Dr. G. Narahari Shastri, Director of CSIR NEIST, to present a valedictory speech. Over to Professor Shastri, sir. Okay, I think due to some technical issue, he was unable to be present amongst us and has got disconnected. So now may I request our chief guest, Dr. Sumer Chopra, Honorable Director of Institute of Seismological Research, Gandhinagar, Gujarat, to provide his comments on IVWGST and also for the betterment of the subsequent editions of IVWGST. Over to you, sir.
Thank you, Hazarika, Ms. Hazarika. Good afternoon to all. I consider it as a privilege to present my thoughts in this valedictory function of the third International Virtual Workshop on Global Seismology and Tectonics organized by CSIR NEIST, Jorhat. I think the theme suggests that it's mainly focused on the undergraduate, postgraduate, PhD and young scientists. And the main purpose is to disseminate the current understanding about the local and regional seismological issues, tectonics, and what is going on in the recent research work in the field of seismology. with some new tools which has been discovered in last few years. And during this, I think 10 to 12 days, a total of 10 to 12 lectures were delivered by well-known experts. The prominent speakers were Dr. Sailesh Naik, Professor Depeng Jao, Professor C.P. Rajendran, Dr. Ghosh, Dr. Sukanta Roy, Dr. Jade, and Dr. Justin from USGS. And the topics were also the widely discussed topics were ranges from the Koina deep drilling to GPS studies in Indian subcontinent, induced seismicity, intraplate seismicity, and the current status of seismic hazard in Himalaya. And the most recent one, the understanding the physics of earthquakes from the deep learning methods. And we all know that now many researchers are applying the concepts of artificial intelligence and deep machine learning concepts in the seismological data, and many interesting outcomes have been there in the recent publication, which we all gone through in the recent editions of SRL and BSSA also. And I'm sorry that due to some prior commitments, I could not able to attend most of the lectures. And in the last week only, I attended few lectures. But I think most of the students and undergraduate and postgraduate students must have grabbed this opportunity and learned new research from experts which may have enhanced their understanding about seismicity in this part of the world. And I'm really glad to be part of this endeavor and enjoyed listening to inspiring lectures, few of the lectures which I could able to attend this, and hope this will be a continuing exercise every year. And I really thank all the organizers for giving me an opportunity to be a part of this virtual workshop. And I think this should be in from next year, as we all know that Corona is now receding. Then from next year, it would be better if we have some physical mode also, because it is for students, it is always beneficial for any workshop to be in physical mode so that they can discuss a lot of things with the experts of different fields. So you can start with physical and online mode, dual mode, and then ultimately go to physical mode. And once again, I thanks and namaskar.
Thank you so much, sir, for your nice comments regarding IVWGST. Now, may I request Professor J.R. Kayal, former Deputy Director General of GSI, to say his remarks on IVWGST 2022 and also say a few words regarding the betterment of IVWGST. Over to you, sir.
Thank you, Vanessa. It is my great pleasure and privilege to be associated with this international workshop. And as every good thing has its end, so today is the end day of this knowledge sharing international workshop. With being I was privileged to chair all the sessions, and being chairman, I attended each and every lectures. I thoroughly enjoyed it. There are two lectures on deep drilling projects, one by Dr. Nayak and one by Dr. Rai. They are just unique projects, and it is of its kind. That is the only deep drilling project in India. We really learned a lot from these two lectures on the physics of the earthquakes, on the geology of the earthquakes, on the geophysics of the earthquakes, and rock properties, and so on and so forth. Then we have learned a lot on crustal imaging. There are 4 lectures on crustal imaging. One was on Nepal earthquake by Dr. Ghosh from USA. One was on Himalayan earthquakes by Professor Mukhopadhyay, Sagarika Mukhopadhyay. One was on Japan subduction zone by Professor Dapeng Jhao, and other one was on Sumatra, anisotropic structure and crustal imaging by Dr. Suryanto. So it was these lectures really enriched us with understanding of the earthquake source zones and 3D structures beneath the earth. Then we had another lecture on physics of the earthquakes by Margarita from USGS. It was again so illuminating for all of us to understand how one earthquake triggers the others, the physics behind it. Then there was an lecture on aftershocks, forecast on aftershocks. That was, I think, a unique lecture, and it was quite successful in that sense that we can't predict main shock, but possibly we can forecast aftershocks. So that was a wonderful lecture on aftershock forecasting. Then there was a lecture by Rajendran, Dr. C.P. Rajendran, on possibility of mega earthquake in the Himalaya. That is a very debatable topic, and I think he has presented very well, and we all learned how the rupture zones in the Himalaya is really, he's one of the most renowned paleoseismologists, and it was a very educative lecture. Then Dr. Chopra gave us a full account of the Gujarat and Saurashtra seismicity, which is a very active zone in this part of the country or in the world. So it was also very educative. And I think if I missed anything, I think I have talked about all the lectures, how they were so much informative and educative class. And ultimately, when we cannot predict earthquake, I think for the sustainable society, what we can do today, I think we are going to listen to that. That is seismic hazard and risk evaluation, analysis of seismic hazard and risk. So we all look forward to listening to Dr. Bommer, UK, and I think without elaborating further, I welcome the last lecture of this workshop, and over to Anchor, please. Over to Anchor, please.
Vanessa, please.
Okay. Thank you, sir, for such wonderful remarks on IVWGST. Now, may I request our keynote speaker for the last session of the workshop, Dr. Julian J. Bommer, who from Imperial College London, who is present amongst us, to say a few words on IVWGST. Although it would be nice to hear his lecture at the end of this valedictory session, I request him to say a few words on this session. Over to you, sir.
Okay, good afternoon to everybody. I have confessed that I have struggled to attend many of the lectures, but I have come to some. I've been very impressed by the enthusiasm and the interest in this very innovative course, and I'm honored to be here today to provide the final lecture, which I hope will be interesting for those who are attending. I congratulate the organizers for putting on such an interesting event, which has brought together so many people, and congratulate also everyone who has attended to make the time to attend all these lectures, and those who've seen it right through to the last day. I hope I can make it worth your while in a short time. Thank you so much.
Thank you so much,
maybe
sir.
finally to say, if I also support the idea that other people have said, while the internet and these facilities like Teams have made a wonderful opportunity to stay in touch in difficult times, there is really no substitute for being together, because the discussions we can have offline and multiple people talking at the same time is really valuable. So I hope future events will embrace that idea of getting together. Thank you.
Thank you so much, sir. Now, would be glad to hear from any of the two participants regarding IVWGST 2022. Would love to hear the experiences during the, of their attending during the lecture sessions. So they may please unmute themselves and share their experiences. So, do we have any participants who would like to share their experience?
Please proceed to next session.
Okay, so with this, we have almost reached the end of the valedictory session. So the next agenda is vote of thanks by the convener, Dr. Shantanu Borwa, who is a senior scientist from CSIR NEIST. So may I request Dr. Borwa, sir, to deliver the vote of thanks. Over to you, sir.
Thank you so much. I am delighted to offer the vote of thanks of this validity function held on occasion on the final day of IVWGST 2022. At the outset, I would like to profoundly thank the Honorable Director of CSI NIST Jorhat, Dr. G. Narahari Sastry, for being the motivation of everything that has transpired over the last 10 days. Under your guidance, we are empowered with the confidence and belief to organize a program of such immense scale and magnitude. I cannot thank Professor A.J. Michael enough for all of his help and assistance since the first edition of IVWGST. Irrespective of his busy schedule, he has been kind enough to volunteer as one of the international advisors of IVWGST. I am also thankful to national advisors, Padma Shri awardee Professor S.K. Gupta, Dr. V.M. Tiwari, Director of CSR NGRI, Dr. Kalasan Sain, Director, Wadi Institute of Himalayan Geology, Dr. O.P. Misra, Director, National Center for Seismology, for their valuable suggestion. I'm equally thankful to Dr. Sukanta Roy, Borehole Geophysics Research Laboratory, and Dr. Sumer Supra, Officiating Director General and Director of Institute of Seismological Research, for their encouragement. My heartfelt gratitude goes to all the keynote speakers for volunteering their time and effort and for being a part of IVWGST. My immense regard and gratitude is also reserved for Professor J.R. Kyle, Dr. Vivit Suranto, Dr. Devajit Hazarika, for being the chairperson and co-chairperson respectively of IVWGST. I would like to extend my deepest gratitude to Dr. Manoj Kumar Fukon, Dr. B.K. Chaudhary, for the assistance being the co-convener of this workshop. I ought to thank and acknowledge the effort of the technical committee members of IVWGST for successful conclusion of IVWGST 2022. And last but not the least, I would like to convey my sincere thanks to all the participants of IVWGST for making this event so successful. I hope the workshop served its purpose and helped you in learning and exploring new concepts of tectonics and seismology. With this, the validity function comes to an end. Now, may I request Ms. Anessa to proceed with the final session of this workshop. Over to Ms. Anessa.
Thank you so much, sir. Now, with this, we have concluded the valedictory session. Now, the last session of this day, before beginning the last technical session of this workshop, let us introduce our today's keynote speaker, Dr. Julian J. Bommer from Imperial College London, who will deliver a talk on earthquake hazard and risk analysis for natural and induced seismicity towards objective assessments in the face of uncertainty. Now, may I request Dr. Timanshu Chetia to read out a very brief and illuminating biodata of Dr. Bommer. Over to you, Dr. Timanshu.
Dr. Timangsu, please. Please unmute.
Yeah, namaste. Am I audible?
Yes, yes, you are audible.
Yes, thank you. Namaste. A very warm good evening from Assam, the land of unity and diversity. It's my privilege, and I take this opportunity to read out the brief biodata of Professor Julian J. Bommer today. Professor Julian J. Bommer is a professor, researcher, and a senior research investigator in Faculty of Engineering, Department of Civil and Environmental Engineering of Imperial College, London. Professor Bommer completed his BSc in Civil Engineering with first class honors in 1985 and MSc in Soil Mechanics and Engineering Seismology in 1986 from Imperial College, London. Later, he completed his PhD on Engineering Seismology in 1991 from University of London. His area of expertise is wide, which includes engineering seismology, earthquake ground motion characterization and prediction, definition of earthquake action for seismic design, seismic hazard assessment for natural and induced seismicity, earthquake loss estimation, and risk analysis. He had successfully supervised 15 PhD students and has imparted his adept knowledge in engineering seismology, risk analysis, professional engineering practice, and energy to understand and undergraduate and postgraduate students. He has won several prestigious awards, such as Euner Memorial Lecturer, Seismological Society of America 2020, Outstanding Paper in Earthquake Spectra 2008, Imperial College Award for Teaching Excellence 2000, Queen's Jubilee Scholarship for the Institution of Civil Engineering 1982. He is also the lead member of Panel of Expert Panel on Seismic Hazard for the Office for Nuclear Regulation 2011. He has published more than 200 papers in reputed international journals, conferences, and seminars. Last but not the least to mention, this was just a concise of his vast knowledge and research vocation. Thank you, Professor Bommer. Now, moving forward with zeal, we look forward to hear your talk. Professor Bommer, may I kindly please hand over to you for your talk. Thank you once again.
Thank you very
Dr.
much.
Timangsu.
Sorry. Should I begin?
Yes, sir, you may take over the digital space and enlighten us with your lecture. Over to you, sir.
Is it displaying on your screens, my slides?
Yes, sir. It is
Okay.
visible.
Okay, thank you very much for the very kind introduction and for the honor of this invitation. I'll begin immediately because my lecture is slightly on the long side. So the title, as has been already introduced, Earthquake Hazard and Risk Analysis for Natural and Induced Seismicity. And what I want to address is the question of how we can get objective assessments in the face of uncertainty. The lecture I'm going to present this morning is a somewhat shortened version of the 17th Mallet Milne lecture awarded to me by the Society of Earthquake and Civil Engineering Dynamics in the UK, which I presented here in London in June. So I'm going to begin, perhaps unusually, with my conclusions and then illustrate them through the following slides. The key points I'm going to try to communicate to you today are, I should emphasize, as I'm coming now as an engineer, more a user of the tectonic information, seismological information that has been discussed in the last 2 weeks, rather than a researcher directly in the field of tectonics myself. I work more downstream, let's say. And the topics I wish to address with you are, firstly, that seismic hazard really has its meaning in the context of seismic risk, risk meaning the possibility of damage, losses, injury due to earthquakes. That the practice of seismic hazard assessment has matured greatly over the last decades, especially with regards to how we can quantify and incorporate uncertainties. Nonetheless, I'll illustrate with a couple of examples only in this lecture, but objective assessment of seismic hazards can still be elusive in some cases because of preconceptions or indeed because of vested interests that have an undue influence on the results or how the results are presented. Then I move on to try to explain how achieving objective assessment of hazards due to induced seismicity can be even more challenging, especially since the processes causing induced seismicity are often in themselves controversial. However, I believe that the well-established practices of seismic hazard assessment can be adapted and applied to induced seismicity, but they do in many cases need to be adapted. And although uncertainties can be high when dealing with induced earthquakes, I will argue that our state of knowledge is sufficient never to require recourse to the precautionary principle. I believe we can manage induced seismic risk rationally, just as we can do for natural seismic risk. The rational management, however, of induced seismicity requires that it be approached from the perspective of seismic risk rather than focusing only on hazard parameters. And I also would like to make the point that induced seismicity can be mitigated in two ways, both through the control of the hazard, an option that's not available to us for natural earthquakes, and through the application of conventional earthquake engineering to reduce vulnerability. So these are the key, what would have been my conclusions at the end. I'm presenting them now and hope to illustrate these in the ensuing slides. So let us begin with the definition of earthquake risk. Earthquake risk is a product of seismic hazard, exposure, and vulnerability. By exposure, we simply mean the built environment, any buildings or infrastructure. Seismic hazard is the focus of engineering seismology, which aims to quantify the demand that earthquakes could impose on the built environment. Vulnerability expresses how likely our structures and infrastructure are to be damaged under earthquake actions, and this is the focus of earthquake engineering in providing capacity to resist earthquake effects. If the demand exceeds the capacity, then catastrophe ensues, and our objective is to ensure that the opposite is true, that the capacity exceeds the demand. So seismic hazard analysis, what's it about? Really, we're trying to estimate or predict what future earthquakes may do. One of the questions is, where will future earthquakes occur, and how large will these future earthquakes be, i.e. what will be their magnitude? The answer to both those questions is related to faults. We know that with the exception of very deep subduction earthquakes are always caused by the sudden rupture of geological faults. So if we locate faults, then we can constrain whether important future earthquakes are most likely to occur. You have two examples here on the right-hand side from Armenia. You can see some figures there to give you a sense of the break, the 2-meter offset, and on the left-hand side, an earthquake in 2006 in Mozambique. The size of the rupture also increases, actually exponentially with the magnitude of the earthquake. So when we encounter and map faults, it can not only tell us where future earthquakes are likely to occur, but their dimensions can indicate the seismogenic potential. What is the largest earthquake that we can expect to occur? And I'll give you a short story about finding earthquake faults in relation to the Diablo Canyon nuclear power plant in Central California, which you can see a picture of here. This is the geology of the region. The DCPP is here. I hope you can see my cursor on the coast. And you can see here a very major structure called the Hosgri Fault Zone, which is what dominated the design. So when this nuclear power plant was built, seismic hazard was still done deterministically, and the power plant was designed to resist a magnitude 7.2 earthquake on the Hosgri Fault, which at its closest point is just 4.5 kilometers away from the plant. That's the design spectra. It's the envelope of those two proposed by eminent experts working in this field at that time. And the design PGA, the anchoring point of this response vector, is 0.75 G. So it's a very considerable level of seismic loading. When the Nuclear Regulatory Commission in the United States issued the license for the plant to operate, one of the conditions they put was that the seismic hazard should be continuously reassessed and the seismic hazard assessment updated, which led to huge investment in seismic monitoring and geological studies and geophysical studies. One of those studies focused on reevaluating the earthquake catalog, which these are the epicenters you can see in this current picture, these gray dots, epicenters located in standard procedures from the United States Geological Survey. When localized velocity models were used and joint location techniques to increase the accuracy, what then happened was we suddenly found quite a rearrangement of these epicenters, and the worrying thing that emerged was this alignment of epicenters you can see here along the coastline, which is labeled SF. And this then transpired to be a fault called the Shoreline Fault, which, as you can see, extends right up to the northwest to join the Hosgri Fault. It was subsequently confirmed by fault plane solutions, all having the common mechanism and other investigations. And so now you've gone from having a fault that was 4.5 kilometers away from the power plant to a strand, potentially a strand of the same fault, now only 600 meters away from the nuclear island at this power plant. So the primary concern now was that the scenario of a major earthquake on the Hosgri fault propagating southwards from north to south and continuing on the shoreline fault, which would therefore would place a magnitude 7+ earthquake just 1 kilometer from the plant, as you can see in that sketch there, that these two would rupture together. So there was quite a challenge for the plant to demonstrate that it would still be safe under such circumstances. The question I'd like to go back to, however, is why was the shoreline fault not discovered previously, despite extensive geophysical explorations? Because a huge amount of money and effort had been already invested. Well, one of the reasons is the fault is actually located in the surf zone, where traditional offshore geophysical techniques run from vessels, from boats. They can't access that couple of 100 meters adjacent to the coast because of rocks and the waves. So there was no direct geophysical measurements there. But the main reason is simply that over the ensuing years, from the mid-1980s to more recent times, there's been an absolutely colossal improvement in the resolution of geophysical measurements. So this is the bathymetry. You can see the power plant here, this black dot, this is the coastline, and this is a bathymetric map from offshore geophysics produced in 1989. This is a bathymetric map produced 20 years later with digital measurement techniques, and you can see now the fault shows up absolutely clearly, perfectly well, which is not at all visible with the resolution of data that was previously available. Okay, coming back to these questions of seismic hazard analysis, we need to find the location of the faults, the dimensions of the faults, but we also need to know how frequently will the earthquakes could they occur. And the presence of faults, therefore, is not sufficient to define the potential source of earthquakes. There must be evidence for slip on the fault during recent geological times, by which we would normally mean the Quaternary period. So we need to find or create exposures of the faults. Here's one in Central America, and you can see the offsets of different strata here. So we need to date those strata to work out how much displacement occurred over different times, and particularly when were the most recent displacements by the dislocation or otherwise of the most recent deposits. And I can tell you a quick couple of stories about finding faults or characterizing faults and how this can be, how important it is to get that right. This is a case from Spain, in the northeastern part of Spain. And in 2012, the government of this region, Aragon, announced a project to build a new public hospital in the city of Teruel. So a very important public service. And they actually had, according to the seismic design code for Spain, this location is in the lowest seismic hazard region of the entire country, and therefore seismic design would not normally be required. But just as the project was beginning, in terms of actual going on to construction, in 2016, a study was published of the Concoud fault, which actually comes within 400 meters of the hospital site, was published. And this publication inferred that this fault was actually slipping at a rate of 0.53 millimeters per year, which is not as fast as, say, faults in California, but is a significant rate. That means in 100 years, we have about 50, we have 5 centimeters of displacement, which begins to accumulate and begins to create an important hazard. So the hospital construction project was suspended, and because of this new information, it was decided that the design would have to be modified and extensively modified to accommodate what appeared to be a much higher level of seismic hazard. So the project was delayed. However, when other people, this was actually done now in the context of a study we were involved in for nuclear power plants in Spain, this fault and several others were studied, and it was found that the geochronology results from the lab that had given these recent movements and given the indication of high slip rates were actually systematically underestimated. So you see here on this plot, the x-axis are the optical luminescence stimulated luminescence ages determined by that laboratory, and here on the vertical axis are the new ages that were done by a laboratory, perhaps performing these tests somewhat more competently. The answer was that these faults were several times older, or the movements were much older than had been inferred, and therefore the slip rate was significantly lower, and therefore the hazard was equally lower. The hospital project was then resumed in 2019, but it had been delayed by 3.5 years as a result of poor geophysical data. Another story comes from Panama, the Pedro Miguel fault, the Panama Canal. So in the early 2000s, work began on a new set of locks to accommodate what are called post-Panamax ships in Panama. In the canal, and at that time the Panama Canal Authority established a seismic advisory board to determine the earthquake loading for new locks and dams. I was privileged to be a member of that panel. At the time we began our work, seismic hazard estimates for Panama were entirely controlled by earthquakes associated with large offshore tectonic structures. The incipient subduction zone to the north and a former subduction zone to the south, which has become a transform zone. Here's the location of the canal, far away from those structures and with relatively low hazard. But as work began under our recommendations and various geophysical and geological teams were brought in, what we began to notice very quickly, looking here at digital elevation models, is very distinct lineaments visible in the topography. You can see several lines, which are always indicative of active tectonic processes. And you can see here, if we look at the map, all the blue here is effectively the canal system. And if we look at this line here and move it backwards, you can see you can realign those mountain ranges several tens of kilometers away to the west, to the east, sorry, showing that in fact this had it was undergoing current and active deformation. So this led to investigations, extensive trenching and mapping of the trenches by various teams of experts. And what they identified were several active faults across the central part of Panama. The most important one being this one, the Pedro Miguel fault, because it comes, as I'll show you here, within a kilometer or so of the Pacific locks, and it's also a short distance from the very busy Panama City. And what the investigations in these trenches showed is that this fault has actually undergone several magnitude 7 earthquakes, the most recent occurring within the last 500 years. So this is was a complete change of perspective regarding the tectonics and seismicity of central Panama. Here's one of the sets of trenches, and that's where the fault roughly runs across it. You can see Panama City in the background there, about 4.5–5 kilometers away. Many of these structures not adequately built to withstand a strong earthquake. So this raised very serious concerns. It also raised a lot of denial that the geological data was reliable. And then we found a piece of evidence was found, which was possibly the most compelling paleoseismological evidence I've ever seen. If we go back in history, this picture on the left-hand side shows a cobblestone road that was used to transport the Camino de Cruces from these two ports on the Pacific coast. Gold was transported by mule to this point here and then taken by river across to here and then sailed over to Spain. So the bringing gold from Mexico, Peru and other places was brought here, crossed the isthmus and then sailed back to Spain. So we know when this road was built in 1533, and we know that it was abandoned around 1855 when a parallel railway crossing was opened. And here is the line that the Pedro Miguel fault would cross. Now, this was discovered after all the trenching work. And here is the site inside. You have to walk a couple of hours through the jungle to get to the site. But that's where the fault would be projected to be running. And what we can find here, the traces of the old Camino de Cruces, is that it's been offset by exactly the same displacement and exactly the same direction as had been inferred from all the trenching work. So we know that an earthquake has displaced this relative in that period of time, which is consistent with the conclusion of the most recent earthquake being in the last 500 years. And it's also known from historical documents that the old Panama City was actually extensively damaged by an earthquake that occurred in 1621, which had always been assumed to be associated with one of the offshore sources of seismicity. But it now turns out that the most likely explanation was that this earthquake occurred on the Pedro Miguel fault, and therefore very close to the new locks and close to the current location of Panama cities. And this was then the basis of the design, final design for the canal expansion, and it got incorporated into, this is the seismic hazard map from the current seismic design code in Panama. You can see it incorporates these active faults. However, even with this compelling information, there was still great resistance. Some engineers have campaigned quite strongly to try and discredit this information and make these faults go away. And they have the advantage that somewhere deep in the Panamanian psyche is a belief that they live in a seismic country. On one of my visits, this was in my hotel room, this brochure explaining why Panama is a lovely place to live or to retire. And in its opening pages, it tells you all the highlights why Panama is a great place to live. And this is the one that caught my eye. It tells you Panama has no hurricanes or major earthquakes. And this is in common, let's say, like popular knowledge in Panama is the case, because these large earthquakes that occur in these active faults are not accompanied by moderate seismicity in between the major characteristic events. And this actually goes right back to the history of why the Panama was chosen for the Isthmus Canal. It was actually chosen over an alternative route in neighboring Nicaragua because of avoiding earthquakes and volcanoes in that country. You can see, if you look at a map, there are actually active volcanoes and major seismicity all the way along the Central American Pacific coast, until we get to Panama, where it's deflected by these offshore, and it would appear that Panama is without active volcanoes or many earthquakes. But this is a short-term record. This is a few decades of seismic observation, and it doesn't reveal what was revealed by the geological record. When the US Senate voted in favor of the Panamanian route back at the end of the 19th century, it was actually attributed to this postage stamp being circulated to all the senators on the morning of the vote, showing them picture on a postage stamp from Nicaragua with an active volcano. So the whole reason for choosing Panama was the idea that it was seismically and volcanically safe. Turns out it's not the case, and it's been quite difficult for some people in Panama to update their vision. The final part of seismic hazard analysis, when we know where each earthquake is going to occur, is what level of ground shaking will they produce at the site of interest, because ultimately the damage is caused by the ground shaking, and therefore we need to study our recordings, accelegrams, and characterize the ground shaking with a series of different parameters, such as peak ground acceleration, or if we integrate our acceleration, we get the velocity trace and can use the peak ground velocity. There are several other parameters as well, but the final part of completing a seismic hazard analysis is developing models that can predict these parameters, because these are what we're actually going to design our structures against. Because we have uncertainty in every single component of a seismic hazard analysis, because our data is simply insufficient to be unambiguously interpreted, even in California, there's nowhere in the world where seismic data is sufficient to be able to unambiguously define where the seismic sources are, what's the right ground motion, what's the biggest earthquake that occur. So we use logic trees, which simply define a node for every component of the hazard input, and then has branches coming from that node with alternatives to which we assign weights that effectively become probabilities regarding how their relative likelihood. This is a very simple logic tree, but it illustrates the purpose. But what we then do is repeat the hazard calculations not once, but for as many different combinations of branches as they are. Each way through the curve, the branches will produce a single hazard curve, the weight upon which will be the product of the weights on the branches. And from these then family of weighted hazard curves, we can develop a distribution of the hazard. So we have here the thick line here is the median hazard. These are the fractiles either side, and the red curve, which is what we usually use, is the mean hazard. But we now have two decisions that we can make. How low the annual frequency of exceedance is, what is our target safety level, which will depend on the type of structure and the consequences of failure, whether it's a simple dwelling or a nuclear power plant, for example, and how far we go across on this axis, which of those curves we use, really relates to the question of what confidence do we want to have that that safety level is being assumed. I could talk a lot more about logic trees, but that I hope is a helpful overview. What we're really concerned is how we get together to make these logic trees, because we have to invoke expert judgment. What the logic trees are displaying is epistemic uncertainty, which is related to lack of knowledge. So its quantification inevitably involves expert judgment. We can't measure epistemic uncertainty from our data, but we can also generally conclude that the outcome will be far more robust if more than one expert makes the judgment. So we would like to have multiple experts judging, making their assessment of the epistemic uncertainty. And guidelines have been written for how to do this, something called the SHAC process. SHAC is the Senior Seismic Hazard Analysis Committee, and they produced a report in 1997, which was updated into more practical guidelines based on actual experience of implementing their recommendations in 2012, and then updated again in 2019. The guidelines were specifically developed for nuclear projects, but they are applicable, I would argue, for any structure in terms of the general principles of how to conduct these studies. So we now have good procedures for how to bring multiple experts together. What I think is perhaps equally exciting is that there have been important advances in the last few years in the methodology to construct logic trees so that the appropriate distributions of uncertainty can be obtained. So it's one thing is to bring the experts together to analyze the available data and models and to make inferences about what the uncertainty should be. But we need to be able to visualize that uncertainty in terms of the parameters, magnitude, location, ground motion, amplitude, that actually drive the hazard level. And in terms of the ground motions, what we have are these equations we call ground motion prediction equations, GMPEs, that predict amplitudes of ground shaking as a function of magnitude, distance, the type of fault, and the surface conditions at the site. So here we have predictions of peak ground velocity against distance for two different magnitudes, showing the dependence on how we classify the site. This is for strike slip earthquakes. And conversely, here we have the same plot, but now it's only for rock sites, and we're showing the influence of the style of rupture, with normal faults generally predicting yielding lower levels of motion than strike slip and reverse. So what we've developed in recent years, which has now become state of practice in these nuclear projects, is what we call the backbone GMPE approach. So for many years, the standard practice, and we still see this in other fields, was to select and weight published GMPs on the basis of their potential applicability to our target region. And that often led to unintended distributions of predicted levels of shaking, because you're simply applying weights to models, but what you're actually interested in is the weights on the distributions of predicted motions. So these are attenuation curves. The solid lines are for magnitude 7.5, the dashed lines for 5.5. They're three GMPs that were used in seismic hazard studies in Canada for major dams. And they're plotted here, the predictions for PGA and for what we call response spectral ordinates at different frequencies, plotted against distance. And what you can see is that at several locations, now highlighted by the arrows, the curves completely converge, which suggests that there's no epistemic uncertainty in the ground motion for that combination of magnitude and distance, which is absolutely not true. It's simply a facet or an artifact of these particular equations. So we want to avoid unintendedly narrow, or indeed in other locations, it might be unintendedly broad distributions. And the way we do this is an approach that's been developed called the backbone GMP approach, where we take a single model and we adjust it to the local conditions in the target region, capturing uncertainty through each adjustment. So for example, we might choose a backbone GMPE, we might make an adjustment for differences in the local region and the original region of the equation for stress drop, for geometric spreading, for anelastic attenuation. And when we put these all together, we'll end up with predictions like this. I've plotted them now for a single distance against magnitude rather than for single magnitude against distance. But what you can see is now we have curves that clearly show a distribution. They're not crossing each other. They're not pinching down to concentrated distributions in any. They always give us an appropriate measure of the spread. And as we should expect, as we go to larger magnitudes where we have much less data and our models are more poorly constrained, we have a better distribution, a broader distribution reflecting greater epistemic uncertainty. And we've also brought this into the same concept into the local site amplification effects in seismic hazard assessment. Now, these GMPs, first a bit of an introduction on how we do that. The GMPs predict site amplification as a function of the average shear wave velocity in the top 30 meters of soil at the site, a parameter we call VS30. So nearly every modern GMP has VS30 as an equation. But here we have two sites. One is clay, one is sand, which, if you calculate their VS30, they have almost identical values of that parameter. And yet their actual profile in the top, their layering structure in the top 30 meters is different. And below that, the structure of these two profiles is very different. So when we actually calculate their amplification factors for the full profile, we see that they're significantly different. Here we've got the median amplification factor plotted against period, and you can see that the amplification factors of these individual sites are quite distinct from each other. So if we use just the VS30 that's in a GMPE, we're only going to get a sort of generic site amplification which represents an average of the sites that have been analyzed, whereas what we really want to know is how is our specific site going to respond. And so we do that by performing when we do site-specific hazard studies, the standard practice now is to calculate the hazard in a deeper rock horizon and then perform seismic response analysis. So here you would see normally we have basement rock, and we would choose either here or higher we calculate the hazard in this rock and then perform site response analysis for the overlying layers to transport the rock motion to the surface, capturing the actual frequency and amplitude characteristics of this specific site. We would characterize the uncertainty in the rock and sand layers being analyzed by having different VS profiles, different profiles of the shear wave velocity. So here we see we have a median, an upper, and a lower. And this is not dissimilar to having different equations. So we assign weights on these VS profiles is not that different from assigning weights on GMPs. It doesn't tell us exactly what's going to be the outcome, because what we're interested in is not the uncertainty in the VS profile. We're actually concerned with the uncertainty in the resulting amplification factors. That's what moves the needle in hazard assessment. So you can see here we've got the amplification factors plotted against period using those three profiles, and you can see the same thing happens unintentionally at certain periods. Our amplification curves now collapse onto each other as if there was no epistemic uncertainty. It's not intentional, it's not true, it's not intentional, it's an artifact. And again, we can avoid this by using a backbone approach where we can get a broad, more complete distribution that always maintains an appropriate level of epistemic uncertainty without this pinching or the curves collapsing. So I think these advances that have been made in recent years are really quite exciting in terms of really enabling us to identify the uncertainties, visualize them, and bring them into the study in a much more effective and transparent manner. But even with such advances, we have to ask the question, can we get objective assessment of seismic hazard? I showed you now in Panama that that's not always the case. So robust assessments of hazard based on the best available data and including all unavoidable uncertainties should provide the starting point for decision making regarding risk mitigation measures. In other words, what are we going to do from an engineering perspective? However, as we saw with the Panama Canal, preconceptions about hazard levels can be obstacles to objective assessments. And I could talk to you several cases where people have tried, let's say, to bring the hazard levels calculated back down to lower levels that they were more comfortable with. But I'm going to show you, because of limited time, just one interesting example where the opposite happened. In the early 2000s, there were two earthquakes in Italy, the second of which, the 5.7 Molise earthquake, caused a number of deaths. In fact, it caused the collapse of a school, which killed 25 children and their teacher. So these two events, you can see on this map of seismic sources, both occurred outside the area of mapped earthquake sources. So they really came as a shock to the Italian, let's say, seismic hazard and earthquake engineering community, because they occurred in zones which were considered almost aseismic. And that raised a lot of concern, obviously, that if destructive earthquakes were happening where earthquakes were not meant to happen, then something needed to be updated. So that began a project to produce a new seismic hazard map, which was actually the first stage of a project to then reassess also the safety of school buildings for earthquakes throughout the country. But I'm going to focus just on the hazard reassessment. So what was done was for over about 2 or 3 years, I was a reviewer of this project. They developed a new seismic hazard map, which is shown here. You can see now the entire country is zoned. Nowhere is left out. And 4 zones were defined. One, the highest zone being the highest hazard. That's the red zone, going down to the light green, which is low hazard, but still not considered a seismic. But Italy's political constitution requires that regions are allowed to have a say in all federal decisions. So this map was derived by INGV, which is the seismological service of Italy. But it was then issued to the regions, who were given a period of time to allow to make changes locally to move any given location by 1 zone. Okay, for which they didn't necessarily have to provide justification. So 69 municipalities were moved to lower hazard zones. Just not very surprising, particularly in the south, in Trento and Sicilia. 69 municipalities, the local regional authorities decided to make them lower hazard. But what was even more interesting and surprising is just before the deadline for submitting these changes, 4 municipalities in a place called Basilicata in the south were moved to higher hazard zones. So they were moved up from zone 3 to zone 2. And this is the area. And you can see these ones here, these 4 municipalities had been shaded yellow as zone 3, but they were moved up to zone 2. So this region voluntarily decided that it would move its own municipalities to a higher hazard region. One of these is a municipality called Scanzano Gionico, and the reason they did this is they had been selected for as the site for a national nuclear waste repository for low and intermediate level waste. And the legislation regarding the repository forbid construction of a repository in regions classified as hazard zone 1 or 2. So at the 2 minutes before midnight, changing the classification of this municipality from zone 3 into zone 2, they managed to kill the nuclear repository site in their region. Okay, that's a condensed overview of treatment of natural earthquakes. I'm now going to move to induced and triggered earthquakes, and how we can adapt and learn from that, what we've done in natural earthquakes. Induced and triggered earthquakes, we could say, are earthquakes whose occurrence in space and time is related to anthropogenic activities that cause changes to the pressures, especially fluids within the Earth's crust. You can see in this illustration, I'm sure anyone who attended Dr. Rubinstein's lecture a couple of days ago got a wonderful introduction to the whole concept of how these earthquakes come to occur. So I won't focus too much on that. But making objective assessments of the induced seismic risk and hazard is especially challenging because these events are viewed by those affected as an imposed rather than natural hazard. If you know an earthquake has an anthropogenic origin, then it's no longer nature that's caused your discomfort or danger, or the danger you feel you might be in. It's now something imposed on you. So people will be opposed to this for that reason. And also because, as I said before, the industrial processes causing the seismicity are often controversial, particularly, for example, if we're talking about hydraulic fracturing for shale gas, for example. So several things we need to do to make sure we manage this rationally. First thing is we have to distinguish natural and induced earthquakes correctly. Many times it's unambiguous, but there are many cases where it's not. There have been important cases where the two get confused, and that doesn't help the science or the management of the risk. So I would say here, for both this science of understanding induced earthquakes and the rational management of induced seismic risk, it's vital to correctly distinguish between earthquakes of natural origin and induced earthquakes. And I quote a paper there in which we propose a scheme for doing that in a let's say, rational and fair-handed way. But equally important in many cases is not only to identify that earthquakes have been induced, but to make sure that they're correctly associated with the actual correct causative process if multiple operations are underway in a region. This paper has just been published in BSSA, where they try to develop a scheme to work out which earthquakes are associated with hydraulic fracturing and which with wastewater disposal. Wastewater disposal involves much larger volumes of fluid injection and has caused much greater induced seismicity. So decoupling the two is really important, both if you want to design a mitigation measure and if we want to advance our scientific understanding of the processes that lead to induced seismicity. So that's a very important step. So I'm going to assume that we have done that, that we know what's we're correctly dealing with genuinely induced earthquakes. So mitigation of seismic risk, that's ultimately what we want to achieve if we're going to enable activities to go ahead that cause induced seismicity. But to do that in a safe way, we need to manage the risk that those earthquakes could occur. So if we come back to our equation of seismic risk, we're understanding risk to be the convolution of hazard, exposure, fragility, and consequences. So previously I had fragility and consequences as vulnerability. Here we separate them. Fragility is the strength of the building, consequences of what happens if the building or structure fails in its operation, which could be injury to the occupants, release of radioactivity for a nuclear power plant, loss of transport if it's a bridge that collapses, etc., etc. Now, for natural seismicity, what we do is we begin by assessing the hazard. We quantify the seismic hazard because it's nature and we have no control over it. And that informs by how much we should reduce the fragility in order to keep the seismic risk down to appropriate levels, depending on what the consequences are for a given exposure. And we can apply that same philosophy to induced seismicity, but we have another option in induced seismicity, which is to reverse this process. We can look at the exposure, what buildings are adjacent in the region where we're operating our anthropogenic processes, injection processes, and we can assess the fragility of those structures, and then we can quantify these, quantify the exposure and the fragility, so we know what's at risk, and then look for schemes to control the hazard so that we keep the risk at the right level. Completely invert the program because we have the problem, because we have the option here, which if earthquakes are induced earthquakes are caused by anthropogenic processes, then modifying the anthropogenic processes can change the hazard. And we do this to what are called traffic light systems. So the idea of a traffic light system is you have to set up a monitoring system, seismic monitoring, so you're measuring with very sensitive network in real time, you're locating and measuring the magnitude of earthquake events. And you set thresholds so that if there's nothing to worry about, you continue. If some seismic events begin to appear that trigger your yellow light, you would begin possibly reducing some of the injections, the volumes, the rates, etc., increasing your observations. If you pass the red light, then you have to immediately suspend your operations. The objective is to avoid induced earthquakes that could be big enough to cause damage to exposed buildings or infrastructure. That's the ultimate objective. It assumes that the induced seismicity sequence will include smaller events prior to the occurrence of potentially damaging events. A traffic light will only work if you have events that will trigger a yellow light and allow you to take some action before you get to the red, or even that stopping at the red light will stop you getting to a magnitude big enough to cause damage. It's also necessary for a traffic light scheme to be effective that the crust will respond rapidly to changes in operation. So it can work well for local fluid injection processes. It's much less effective if the fluid is gas, or if you're related to gas extraction, for example, or to impounding of large reservoirs. So the traffic light scheme option is not always appropriate, but in many situations, geothermal projects, wastewater injection, potentially hydraulic fracturing, it can be a very effective tool in ensuring we don't reach earthquakes, which would be problematic. The very first traffic light that was at least that was developed and published was for an enhanced geothermal project in Central America and El Salvador. I was part of the technical team which did this project. So you see here, this is the area that was to be simulated by high pressure injections into hot rock, and all the little squares here are locally exposed houses. There was concern keeping them safe. So what we did is we worked out what were the PGV levels, peak ground velocity levels that would cause damage. We assumed these would occur at the depth, the earthquakes would occur at the depth of the injections and directly below the houses, and therefore we could calculate what, by having PGV thresholds through a GMPE, we could convert these back to magnitude, PGV equivalent magnitude, and we defined green, amber, and red levels based on different responses to the levels of motion that could occur. And we put basically this line here reflects the background natural seismicity. So provided we never exceeded the background seismicity, you'd have to assume that was green because you really hadn't changed anything. These are the actual observations that were made during the early stages of the operations. So the injections did cause a number of small magnitude earthquakes, mostly less than 3 directly. These are the ones directly clustered around the injection well. They were very closely correlated with the injections in space and time. In fact, on this plot, you can see here the solid line is the cumulative volume of water that was injected, and the dashed line is the cumulative seismic moment of those induced earthquakes. So the correlation, this is a case where it's absolutely unambiguous that you're inducing earthquakes and how closely they're controlled by the anthropogenic operations. However, the largest earthquake, which is this one here, some distance away from the actual injection well, you can see there, occurred during one of the periods when the injections were shut down. And it's not been plotted on here because it was not part of this cluster around the well, but it actually would plot right off the scale in terms of its moment magnitude. It was a magnitude 4.4 earthquake that occurred when pumping wasn't happened. And this raises questions about the validity or effectiveness of a traffic light system, because if your largest earthquake occurs when you're not pumping, the traffic light system doesn't any longer give you a mechanism with which to change the operations to avoid that occurring. So these so-called trailing events, large earthquakes that occur after shut-in or pumping, have actually occurred in many projects, hydraulic fracturing projects and geothermal projects. And they raise the question, if the largest earthquake can occur when injections have already been suspended, is a traffic light system of any use? Well, we addressed this in a paper called Green, Yellow, Red, or Out of the Blue. And what this is an analysis of 35 case histories of traffic light systems deployed in China, Canada, the UK, and the US. And what we did is study what were the kind of magnitude increases seen in these trailing events. And you can see that of those 35 cases, actually the majority don't have trailing events, but when they do, we can see the kind of magnitude distribution they have. The largest jump has been 1.6. So the idea of providing data like this is it can inform your design of the traffic light system. So you can, depending on how much safety you want, what part of that distribution you feel you should be on, or if you feel any of those cases are at all analogous to your own operations, both in terms of the type of operation, the region, and the formations being targeted. But we could say that the red light should be the limiting magnitude we would ever want to reach, minus this delta M of the trailing magnitude increase. So M limit would be the magnitude of earthquake that would lead to unacceptable consequences. So we would incorporate the potential for these trailing events into the design of our traffic light system, rather than being simply surprised that it was exceeded afterwards. These are levels that have actually been used globally. These are all from North America. These are mostly for hydraulic fracturing. You can see yellow light usually around magnitude 2, and the red lights usually in the region of 3.5 to 4. An outlier all of this was the United Kingdom, which after the first earthquakes occurred during shale gas fracking in 2011. A study recommended a red light threshold of 0.5, which is a remarkably low number. It's actually a number of magnitude that the National Seismic Network could not distinguish between a 0.5 and a 1. It's such low levels of motion. What happened as a result of that is that when operations were resumed, the operations were interrupted continuously, and fracking was on the news every couple of days because we had news reports like this. The energy firm said it would halt fracking for 18 hours after a tremor of 0.8 magnitude. A 0.8 magnitude could not be felt even by someone standing directly above it. So it's unrealistically low level to try to operate that. And this is now going to be reversed. I'm actually participating in a meeting in about 10 days to discuss. The moratorium on fracking has just been lifted in the UK, and we're going to be discussing what would be a more rational setting for the thresholds to allow the operations to proceed safely, but actually to proceed. So when we come to M limit, what's the largest magnitude we'd ever want to get to? We really could ask the question, trying to ask the question, what's the smallest earthquake magnitude that can actually cause damage? And to answer that question, we compiled a global database of earthquakes in the region from 4 to 5.5, for which there were reports of damage, economic loss, or injuries. Now, these are natural rather than induced earthquakes. When we try to interpret the data, reports and classifications of damage are often ambiguous. Severe damage may mean one thing for one reporter and something for someone else. So what we tried to base our final analysis is actually reports of casualties, because obviously death is an unambiguous classification. We excluded heart attacks for reasons we explain in the paper. Just an for which we found very many interesting papers in the medical journals about heart attacks and earthquakes, but we excluded them from our analysis. And you can see the data here. You've got the number of people who died as a cause of an earthquake against the magnitude. And you can see that below magnitude 4.5, there are very few cases, and they are all related either to mining accidents or landslides. Now, we know that landslides can occur even without earthquakes, so that's not necessarily a reliable indicator. It might just be people are on a very vulnerable slope after heavy rainfall, and the slightest perturbation would have caused the accident. In the case of the mining accidents, it's very likely that these were major mine bursts, which are actually what's been recorded as an earthquake. So it's not that the mine collapse was a response to an earthquake, but actually was the earthquake. That may even be true in the case of the landslides. There are several cases of landslides being recorded on seismographs and even located and given equivalent magnitudes. So if we look at this kind of data, it suggests to us that for earthquakes smaller than 4.5, significant damage is unusual and would generally be associated with buildings of extreme vulnerability. Another way we could look at this is to look at more robust structures like dams, and here we collated data which is reports of dam performance in earthquakes. So you have magnitude of the earthquake, distance across the other location, how far the dam was from the earthquake, and you can see we'd only really be interested in the color symbols which are damaged. The open symbols are either no damage or minor damage. And you can, okay, above 6, we start to get damage, and that shouldn't surprise us. But you can see here, even around between 5 and 6, we get only damage in very susceptible structures, tailings dams, masonry structures, or hydraulic fill dam, which is a very susceptible kind of construction. When we presented this was actually part of a regulatory hearing in Canada in relating to fracking operations in proximity to a dam. It was pointed out, so just to say that the 4.5 threshold as a threshold for where damage would be expected to occur, again, seems reasonable here, if not conservative. But when we presented this, it was pointed out that there was a case history here, that the Sharadush Dam in Albania had failed in 2009 following an earthquake of just magnitude 4.1, which occurred almost adjacent to the dam. So it made me really curious to look into this case history because it didn't fit the rest of the data at all. So I managed to contact engineers who'd worked on this dam, and what it turned out is they'd undertaken studies of all dams in Albania as part of a World Bank project and had assessed this dam as being extremely vulnerable prior to the earthquake. It had been raised a few years earlier with no benching for embankments. They just put new material on top of the material. They created a slip surface, and they also created incompatible drainage material such that the fines were being continually washed out of the dam surface. Sinkholes were appearing, and it was beginning to collapse. And in fact, a couple of years prior to this small earthquake, they'd recommended $70 million of remedial work to be undertaken on this dam to keep it safe, work that was never undertaken. So the fact that the earthquake did cause the damage you can see here is really something, they're simply accelerating something that was going to happen sooner or later anyhow. Again, we come back to that 4.5, an earthquake smaller than 4.5 will only damage a structure if it's extremely vulnerable, not if it's been well built. So based on observations from tectonic earthquakes, we could propose magnitude 4.5 as a reasonable threshold, unless there are extremely vulnerable structures present. But then the question will come back from people, but these are tectonic earthquakes. Induced earthquakes are much shallower. They're much closer to the ground surface. Surely we would expect induced earthquakes to produce much higher levels of ground shaking, even at the same magnitude. And it turns out that's not the case. These are intensity data from at the top natural earthquakes, and in the bottom induced earthquakes in central and eastern United States, with the intensity data developed by Susan Huff from the USGS. And what she showed with that study was that in the epicentral area, the intensities for natural and induced earthquakes are very similar if the earthquakes are of the same magnitude, despite the differences in depth. And the difference, as explained in this paper by Gail Atkinson and others, they say natural induced events have similar average intensities within 10 kilometers of the epicenter, a consequence of two focal depth effects that have offsetting impacts on the strength of the ground motion. The epicenter is near the source for the shallow events, so the hypercenter, that should say, is the source of the earthquake is closer to the surface. That makes the motions stronger. But the stress parameter, the stress drop, how intensely the rupture radiates high frequency motion, also scales with focal depth and becomes smaller at shallow depth. And these two effects largely cancel each other out. So she concludes, for moderate earthquakes in the same region, magnitude range we looked, induced and natural events have similar intensities and thus equivalent damage potential at distances close to the epicenter. So our conclusions about, if our conclusion at 4.5 is a reasonable threshold for natural earthquakes, it should therefore also hold for induced earthquakes. Some small to moderate induced earthquakes do have high amplitude motions. I'm not denying that. In that 4.4 event in the geothermal project in El Salvador, in Berlin, we had this level. These were the recordings of ground motion in that almost directly above the epicenter in that earthquake, and they actually had 0.8 G. PGA, but no damage to local buildings, even though you can see these buildings are far from being robustly built. The reason is that even though you have an isolated high peak of acceleration, you have extremely short duration. You have barely 0.1, 0.2 seconds of strong shaking, and therefore the energy content of this motion is simply insufficient to cause damage. In fact, when we do probabilistic seismic hazard assessment, we impose a minimum magnitude, and it's there precisely to stop inflating the hazard with such peaks that would increase the level of PGA, but associated with ground motions that are insufficiently energetic to cause damage. And ultimately, the capacity of ground shaking in the epicentral region to cause damage is controlled by the energy of the shaking. And the energy of the shaking is controlled primarily by the earthquake magnitude. And as I said, large PGA values from such small earthquakes are the reason for imposing M-min in probabilistic seismic hazard assessment. So here's a plot everyone's familiar with. It shows earthquake magnitude on the x-axis, and what I'm showing you on the y-axis is the energy released in the form of seismic energy, the energy that causes shaking. But I've normalized those to the energy that would come from a 4.5 earthquake. So you can see a magnitude 7 earthquake, it generates about 5,500 times more energy than a magnitude 4.5 earthquake. But if I take just the range from 2 to 4.5, which looks like a flat line, and plot it by itself, it's equally exponential. It's not flat at all. So we're saying 4.5 is the energy level. You can see here 1 that we can expect to cause damage in anything other than extremely vulnerable structures. And I'm going to talk you through 3 case histories. Castor in Spain, 4.2, which has about 30% of that energy. The Basel earthquake in Switzerland, 3.2, which has barely 3% of that energy. And Groningen in the Netherlands, which again, I don't know, maybe 5 or 6% of the energy of what we would call a normal threshold for damaging earthquakes. So the Castor storage plant occurred in Spain. It was a depleted oil reservoir, and it was decided it would be an excellent place to store gas. Spain mostly imports liquid natural gas from North Africa, and in the winter months, it needs a reserve supply. So 20 kilometers offshore was this reservoir, this disused oil field, and it was set up to be a gas storage plant. When the gas injections were progressing, a series of earthquakes occurred. They were temporarily very closely related with the gas injections, and they occurred in between September and October 2013. You notice on all these figures I'm going to show you this line, which is labeled as the imposter fault. It's going to come back to the question of correctly identifying our faults. The largest event that occurred was magnitude 4.2, as I just showed you on the previous plot. An unpublished report that was produced by the National Gas Company in Spain, which was commissioned by them, although it's actually a private company, after the earthquakes. This unpublished report produced by academics from the US claimed that the earthquake occurred on the imposter fault, and moreover, that this large structure you can see mapped here was capable of generating an earthquake as large as magnitude 6.8. So their report made two important claims. The imposter fault is what had been triggered to cause these induced earthquakes, and that if the gas injections continued, there was a danger of triggering a 6.8 earthquake. And that report led to the project being shut down. In fact, that map of the imposter fault is entirely incorrect. It was based on a single geophysical seismic line being misinterpreted in a PhD thesis and linked with other structures. There is no such structure. When it was reanalyzed, this is the orientation and length, and even that is open to question. But that structure, which they claim could cause a 6.8 earthquake, doesn't actually exist. That report was never published in the open literature, but all the published papers, of which there are now, I think, 10 or so on the Castor sequence, all agree on that all the events, they all agree. They have differences in mechanism, location, etc., but they all agree that the events occurred on small faults below the gas reservoir, and they all state unambiguously that the imposter fault didn't participate in the rupture. The fault is actually a shallow listric structure. It would appear that at about 3.5 kilometers it becomes a detachment surface, and it may even not be a tectonic fault. It may be associated with salt tectonics, so it may not be a seismogenic structure at all. In terms of impact, 4.2 earthquake is getting towards where we might expect damage, but it was 20 kilometers away from the coast. The National Geographical Institute in Spain, the Seismological Service, evaluated the maximum intensity of shaking on the coast to be intensity 3 on the European intensity scale, which says no damage, and the earthquake is felt indoors by a few. People at rest feel a swaying or light trembling. So it was hardly a catastrophic event, and yet there were significant claims for damage. No evidence was ever produced to show those damage, no photographic evidence. But as a result of the popular, let's say, or unpopular response to what occurred, the two technical directors of the Castor project were put on trial with charges that made them responsible for the earthquakes that happened and for larger earthquakes that may have happened. So that 6.8 earthquake that may have happened, they were actually put on trial as for effectively being reckless, that they could have generated a 6.0 earthquake and what that may have done. If they had been found guilty, these gentlemen who were trying to provide a service to Spain in terms of additional gas storage, which it sorely needs, would have been condemned to 7 years in prison. I was actually called to an expert witness in their trial, and I'm very happy to say that a few weeks after the trial, all the charges were dismissed unconditionally. What was most interesting was this was in the lobby of our hotel as we were leaving to attend the tribunal the next morning, the day after the authors of that unpublished report had given testimony. And what it says here, the headline, expert discount the imposter fault as the cause of the earthquakes. So our work had largely already been done, that the authors of that report, when under oath and being cross-examined in a tribunal, admitted that it could not have been the imposter fault that caused the earthquake. And therefore this idea of the 6.8 magnitude event was actually dismissed. Very unusual. Okay, I'll move to a second project, the Basel Deep Heat Mining Project. This is another geothermal project. It was a $60 million investment of the Canton of Basel to simulate fractures in hot rocks. The objective was to create an enhanced geothermal system that would provide renewable electricity to 10,000 homes and heating for 2,700 of those homes. It was located here on the border of Switzerland, Germany, and France. It was about 4.5 meter in high pressure injections into very hot rock. Cold water would be then pumped down into the fractured rock, hot water pumped up and into these heating electricity generation systems. Because of the heating requirement, the project had to be located in a densely populated area, which was somewhat unfortunate. You can transport the electricity over reasonable distances, but there's no way to transport hot water over any kind of distance. So the deep heat mining project was in downtown Basel. On the 8th of December 2006, an earthquake of they developed a traffic light for this project, which was, if you like, somewhat cautious interpretation of the traffic light we developed in El Salvador. An earthquake occurred on the 8th of December, 2.6 magnitude, which passed their red light, so they immediately suspended pumping. And again, we had a trailing event, an event occurring after shutdown, shut-in of pumping, occurred a few hours later. It was local magnitude 3.4, moment magnitude 3.2 occurred, and that shut the project down. Here you have a shake map of that event, the location of which is shown as the red star. There was a dense network of recording instruments installed by ETH Zurich. Maximum PGV was 2 centimeters per second, maximum PGA is 0.1 G. So these were not onerous levels of ground shaking, just like this was not an onerous magnitude. However, the shaking led to $9 million of insurance claims for damage to buildings in the city of Basel, which were paid without on-site inspection. So the city of Basel instructed the insurers to pay these claims without any challenge to actually inspect the damage in order to avoid any political consequences and subsequent legal battles. So I think there was a threshold put that if your claim was below a certain level, it would simply be paid. And the claims came flooding in and added up to 9 million. Here are photographs I managed to obtain of some of those damage claims. And because we're short of time, I've highlighted them for you because they're really quite difficult to see, but they are all essentially hairline cracks in plaster, which may have existed prior to the shaking. One of them was even for this split in the wooden column, which is obviously due to drying of the timber and nothing to do with earthquake shaking. Here again, legal case. Although he was the leader of the project, Marcus Hering was actually contracted by the city of Basel to undertake this project. He was actually put on trial again for this supposed recklessness. He was charged under Swiss laws that forbid deliberately causing landslides and floods. So he was absurdly charged with causing underground landslides and floods. It took the judge a couple of hours to dismiss the entire case, and the prosecutor of the case went straight into retirement. But then the canton of Basel commissioned a risk study, and the risk study was to do what was the risk associated with resuming the geothermal project. And what they did was they made a sort of hydrogeomechanical study of what could be the largest earthquake. I think they came up with 4.5, right on our threshold. But they then estimated the impact that that earthquake, such a hypothetical earthquake, would have, not by physical modeling of the risk, but by simply scaling up these supposed insured losses from 2006. So they took an unrepresentative measure of the impact of the 3.2 earthquake and translated it into astronomical potential damage from a magnitude 4.5 earthquake. And that led to the decision to close the project permanently, and it was abandoned. This was a major backward step for the whole geothermal industry globally. Very interestingly, however, a geothermal project did go ahead in Switzerland, on the other side of Switzerland, on the northeastern side, a few years later in a place called St. Gallen. And this project also caused an earthquake, slightly bigger magnitude. And a comparison was made. So you had two earthquakes, magnitude 3.4 in St. Gallen, 3.2 in Basel. They were at similar depths, somewhere between 4 and 5 kilometers. And these are the levels of motion. The average level of motion here, this black curve from Basel, and slightly higher levels of PGV in St. Gallen. So the St. Gallen earthquake, if anything, was a very similar but slightly more severe event, and yet there was not a single report of damage or claim for damage in St. Gallen. which really does raise questions about what happened in Basel. Finally, my last case history is the Groningen gas field in the Netherlands. It's shown there in the north of the Netherlands, that grey area. It's discovered in 1959, the 7th largest gas reserve in the world. It's still in 13th place, even though it's 75% depleted. It's operated by a joint venture of Shell and ExxonMobil called the NAM. The reservoir is located here in a sandstone at 3 kilometers depth. And you can see that the reservoir is offset by several ancient, really ancient geological faults that haven't moved for hundreds of millennia. This is the mechanism. What's happening is as the gas reservoir compresses due to the depletion of the gas pressure, where the fault is offset, this sets up a stress, a differential stress across the offset, and this has caused some of these faults now to reactivate and to slip. Here we've got on this plot, we've got the date, and here we've got the total reservoir compaction. This is the maximum compaction, the solid gray line here. This is each point is plotted at the compaction at the epicenter. And what we can see is there had to obviously be some threshold level of compaction before any of the earthquakes occurred, because production began in the early 1960s, but in 1991, first earthquake occurred, and then several other earthquakes have since followed. So that was the very first one. We had an important event in 2006. This is really interesting. Magnitude 3.5 earthquake occurred in, it led to about 400 damage claims, about 2/3 of which were paid out, and everyone, it was carry on as normal. There was no discussion anywhere that the field should be abandoned or shut down. And then another earthquake happened, fractionally bigger, magnitude 3.6 in 2012, the Hausinger earthquake, and everything suddenly changed. So the Hausinger earthquake became the game changer in many people's eyes. But the maximum recorded PGA in this earthquake was 0.08 G. You know, I talked about 0.8 G in El Salvador being recorded. This was 0.08 G, and not much bigger than the 0.05 G that had been recorded in 2006 earthquake. And the duration of the motion here in the Hausinger earthquake is about half a second at most. The intensity map, which is based on people's own reports, so it's possibly biased high, but the highest intensity they reported was intensity 6, which would, when it comes to damage, talks about damage of grade 1, this is hairline cracks, to many buildings of vulnerability class A and B. Class A and B vulnerability really is talking about adobe and rubble masonry, houses that you wouldn't expect to find in northwestern Europe. And yet things really took off after this event. And what we see here is number of damage claims against date. This is when NAM was operating, managing those claims. They've since been outsourced to different government-appointed bodies. The red lines are earthquakes of magnitude higher than 2.5 if they're dashed, higher than 3 if they're solid. And you can see there's only nominal correlation between earthquakes and changes to this curve showing cumulative number of damage claims. Here's the Hausinger earthquake, and claims followed. But the claims really took off after the regulator issued its own report at the end, in the beginning of 2013 on the earthquake, claiming that the earthquake, much larger earthquakes could be expected, and really bringing the induced seismicity to a different level, almost creating a crisis where one hadn't really existed before. And you can see then the whole rate at which claims are made now takes off and follows a pattern that's almost independent of earthquakes, just a steady state where people feel they can come forward and claim. Then there's another sharp increase in the gradient here when the government told the operator you must not only honor people's damage claims, if you've damaged their houses, you have to do something to improve their houses, which actually always was interpreted as install solar panels. You can see that led to a very significant increase in the rate of claims when the company NAM eventually managed the government to reverse that decision. The claims rate went back to previous levels. But in recent years, they've taken off again at astronomical levels, even though the last significant earthquake was in early 2019, but it wasn't as large as the Hausinger earthquake. So something unusual is happening there. Interestingly, after the Hausinger earthquake, the operator basically initiated an incredibly intense campaign of data collection to characterize the earthquake, the induced earthquakes and the resulting hazard and risk. They measured subsidence through GPS, INSAR, and conventional leveling to get a real control on how much the field was compacting. They took extensive rock cores from the reservoir at 3 kilometers. Taking a rock sample at 3 kilometers is not an easy thing, I'm sure you appreciate. These were tested statically in the Netherlands and then taken to Japan for dynamic testing, so they could actually be tested how the faults in the reservoir are likely to be slipping. An enormous network of 80 plus new accelerographs, the G network, was installed. These are accelerographs with instrumented boreholes with geophones at 4 different levels down to 200 meters, and every single one of these sites had the shear wave velocity profile measured. And the biggest or most impressive, one of the most impressive investments was to reconstruct full-scale houses using Dutch materials and Dutch builders in shaking tables in Italy and Portugal, and these then tested dynamically to observe dynamic damage patterns and responses in order to calibrate fragility functions. The purpose of doing all of this was then to build a risk model that would start with gas production, predicted compaction of the gas reservoir, a seismogenic model for then what earthquakes would be triggered, the ground motion prediction, including site response, a model of the 150,000 buildings in the region characterized by their fragility or strength to then be able to do a full risk calculation. And very sophisticated risk calculations were done showing the local personal risk, the number of buildings exposed, comparing these with Dutch safety norms. The real purpose of the risk modeling, however, was not only to quantify the risk, but actually to allow exploration of the impact of different risk mitigation strategies, both reduced production and building strengthening. So here, a traffic light would be of little use in this situation. But what we could look at with this risk model is combining certain reductions in the production levels with targeted strengthening up interventions in a given number of the buildings to see which would bring the most effective reduction in risk while maintaining some level of gas production. Despite all of that, the Dutch government has decided to close the Groningen field at the end of the current gas year, which will be in October of this year, in fact, next month. This has significant implications, one of which is, although it's been a profitable resource for the shareholders, the most 90% of the gross income from the field goes to the Dutch state. That's 1 trillion euros today, and at current gas prices, there's still another €1 trillion waiting for the Dutch government in the reservoir, which will no longer be accessed. Another strange feature of this is that the Groningen gas is low calorific gas. It contains about 14% nitrogen. So everyone who uses Groningen gas in the Netherlands and neighboring countries has their burners specially calibrated to use this low calorific gas. Now, to import good gas from overseas, a plant has to be built for about €250 million, which will mix nitrogen in with the high quality gas coming from overseas in order for it to be burnt within the Netherlands. That plant is currently delayed, which is delaying slightly the shut-in of the field, but the carbon footprint of the imported gas, due to its production, transport to the Netherlands, and the nitrogen mixing, will have a significantly larger carbon footprint than the continued use of Groningen gas. There is no realistic plan to replace Groningen gas with any kind of renewables in the short term, especially as we go into winter. And of course, the replacement gas is coming from Russia. The decision taken before the invasion of Ukraine, but now when Western Europe wishes to become independent of Russian hydrocarbons, this is a decision which is now being hotly debated, and there is quite a lot of pressure not to close this field, given that the largest earthquake that has occurred was 3.6, and studies suggest that the level of risk is eminently manageable through targeted intervention of in the weakest, most vulnerable buildings, and together with careful monitoring of the production levels. So I have raced through that. I've presented a great deal of information, but it's a fraction of what was in the original lecture. The lecture was published as a 245-page paper, which is freely available from it's open access. So if anyone is interested by what I've said, you can access the content of, you can access that paper from the Bulletin of Earthquake Engineering. It was published in this year in, well, not in, as issue 6 of this year's volume, and that's freely available. And with that, I thank you very much for your attention.
Thank you so much, sir, for such a wonderful and informative lecture. Now, may I request Dr. Sumit Chopra, sir, to say a few words on this lecture. Over to you, Dr. Chopra, sir.
Thank you, Professor Bommer, for such a nice presentation regarding seismic hazard and risk involved. And you wonderfully started with seismic hazard assessment. Then you introduced a new backbone approach for reducing the uncertainty. Then about the induced earthquakes, how they affect our, you can say, our planning, and how they affect the, you can say, insurance claims and other things. And then you introduced us to some very interesting case studies from Panama, Spain, and from Switzerland, and also just some information about the minimum threshold magnitude above which we can expect a damage during an earthquakes, and for the structures also like dams also, what will be the minimum magnitude above which we can expect a damage. So overall, it was very informative for me and for persons who are working in seismic hazard assessment also, because we are also in Gujarat region. We are also very worried about the induced earthquake, but here it is not induced by anthropogenic activities, but it is induced by some through natural processes. Means we call it a monsoon induced seismicity. So it is the maximum magnitude which we have recorded till date in last 15 years of our dense monitoring in this region. We have recorded a magnitude up to 5.1 maximum magnitude, and that too happened twice in the last 15 years. So, and a lot of hundreds of small earthquakes varying in magnitude between 1 to 2 we are recording every year after intense monsoon activity for 2-3 months. So we are quite worried how to, you can say, how this will affect the seismic hazard, overall seismic hazard of this region. So after listening to your lecture, I think we may have some solution to this problem. But I really like your, you can say, your backbone approach. I may read in detail how to implement this backbone approach in our analysis, hazard analysis. But really, it was a very interesting lecture. And for people who are directly involved in the seismic hazard and risk assessment, this was really an eye opener for every one of us. So thank you very much for this very informative lecture. Over to you, Hazarika.
Neha, please unmute yourself.
Okay. Now, may I request our session co-chairperson, Dr. Vivit Suryanto from UGM, Indonesia, to say a few words on this lecture. Over to you, sir.
Thank you, Hazarika. Good afternoon in Indonesia, Professor Julian Bommer. It is very nice to join this lecture. It's very complete and comprehensive, and you show very detailed explanation on seismic hazard assessment, how it carried out, and how to handle the GMPE and also the PS30 by using the backbone approach. Also, you show very clearly about handling the uncertainty on hazard map, scientifically and also politically, from political, and also how to mitigate the decision on whether the earthquakes is from induced seismicity or it's from naturally occurred by traffic light scheme, and
thank you very much for telling the story about the Basel, the Basel project. I have a colleague working in ETH Zurich as seismologist, and he tell me about the story, but I don't know in more detail. You show us a lot information. And finally, I'm interested about the threshold for magnitude threshold for earthquake causing damage. You tell us that it's about 4.5 something. But I use all information around the globe, or for example, is it also include the data from maybe Japan or also in Indonesia, which is also a lot of quakes happens.
Sorry, was that a question?
Yeah.
Sorry, the sound broke up a little bit. I didn't hear you the question clearly.
About the earthquake threshold causing damage.
Mm-hmm.
Is it 4.5 something?
Yes.
And is it using global information of earthquakes and?
Yes. So this is based on all sources of information we could find where there is a report, even if it's unsubstantiated, where there's reports of damage or loss being caused by earthquakes in that magnitude range. Obviously, we're limited by some cases by language and accessibility to reports, but it's global from the point of view.
Global,
yeah.
So thank you once again, Professor Bommer. It's very nice to see you here, and thank you very much.
Thank you, sir. Thank you, very kind.
Thank you, sir. Now, may I request Dr. Manoj Kumar Fukon to say a few words on this lecture. Over to you, sir.
Thank you, Dr. Bommer, for such a illuminating lecture. It was really nice for us to learn many things from you. But I just a small query. You have once mentioned that in case of Panama, there are very few intermittent smaller earthquakes in between two large earthquakes. But usually we observe a lot of intermittent earthquakes between two large earthquakes. What is your opinion in this regard, particularly in case of Panama? Why there was so much less amount of number of smaller earthquakes in between two large events?
Yes, it's a good question, because it's an unusual but not unique situation. So there are three recurrence models. One of course, the Gutenberg-Richter model, the classic, with a full range of activities from large to intermediate to small earthquakes. Then you have the characteristic model, where you have the Gutenberg-Richter for smaller magnitudes and a characteristic geologically based model with higher recurrence rates for these quasi-periodic events on large faults. But there's also a model being proposed by Steve Wednewski from Nevada, which calls the MMAX model, which has only the characteristic earthquakes on the faults without background seismicity. I would presume the reason is the configuration of faults is such that the crust is broken in this region only by these very large faults, and there's not a great deal of smaller structures that can liberate the intermediate earthquakes. So you have all of the strain is released on these large earthquakes by large earthquakes periodically, with very little or almost no detectable activity in between.
Thank you, Professor. This is just another query. You have mentioned that the damage threshold of earthquake is usually 4.5 or larger. But you have also said that in the last gas field experiment, that maybe some damage were caused by 3 or 3.5 magnitude earthquakes. So how do you explain it?
So two things. One is we're talking about damage. So when I talk about damage from 4.5 earthquakes, I'm really talking about damage that could pose a threat to the safety of a structure or to people. Whether or not damage has been caused in Groningen field is open to discussion. There probably has been damage, but it's going to be mostly what we would call DS1, which is hairline cracks, and occasionally DS2, which would be a little slightly larger cracks or spalling of plaster. But again, not structural damage. What we've found is that most of the damage in the Groningen field is actually caused by settlement. It's extremely soft soils. Most of the area is covered by peats and clays, and with the buildings have rather poor foundation configurations, so the buildings are suffering settlement damage, which may be slightly exacerbated by the shaking, but there's no serious damage has been caused directly by the ground shaking.
Thank you very much.
You're
I really
welcome.
appreciate it.
Thank you. Nice questions.
Thank you so much, sir. Now, may I request Mr. Chandan Dey, Senior Research Fellow at CSIR NEIST, to deliver the vote of thanks. Over to you, Mr. Dey.
Thank you, Anvesha. Honorable Chairperson, Co-Chairperson, keynote speaker, special guest, convener, the co-convener, and all the esteemed participants. I am immensely delighted at the prospect of delivering the final vote of thanks of IVWGST 2022. The past 10 days have been an incredible journey of knowledge sharing and integration. If I were to draw some seismological analogy, the workshop was a great event, or perhaps even bigger. I mean, with the rupture zone, or rather the knowledge rupture zone expanding across several countries, it surely has to be a great event. And look at the stress drop. I, for that matter, thoroughly enjoyed all the sessions, breaking the monotony of my regular schedule and learning diverse concepts of seismology and tectonics. Coming back to proposing the vote of thanks, first of all, I would like to thank Professor Julian Bommer for the absorbing session. What a befitting tribute it was, being the last session of IVWGST 2022. We were glued to the screen, learning about the nuances of earthquake hazard due to natural and induced seismicity and exploring the food for thoughts. Along with Professor Bommer, I would like to yet again thank and acknowledge all the other honorable keynote speakers for volunteering to be a part of IVWGST 2022. I am sincerely thankful to Dr. Sumay Chopra sir, officiating Director General and Director of ISR Gujarat, for being the special guest for today's session. With remarkable scholarship and experience in the field of seismology, your presence augmented the aura of the workshop. Moving on, I would like to solemnly thank the Honorable Director of CSIR NEIST, Dr. G. Narohari Sastry sir, for incentivizing the idea of hosting this workshop and inspiring us to pursue this endeavor. I am thankful to Professor Andrew J. Michael sir, Professor Daping Zhao sir, Professor Ellen Kafka sir, for dispensing your vital roles as the international advisor. Profound acknowledgement also goes out for Padma Shri, Professor Harsh Gupta sir, Dr. V.M. Tiwari sir, Dr. O.P. Mishra sir, and Dr. Kalachan Sain sir for being the National Advisor of IVWGST 2022. I have no words to thank Professor Kayal sir for being the session chairperson, Professor Vivek Suranto sir, and Dr. Devajit Hazarika sir for being the co-chairperson. It was an honor and opportunity for us to share the digital space with luminaries like you. Further, I'm immensely thankful to Dr. Santanu Borua sir, the convener of the workshop, for putting your shoulder to the wheel, both from the perspective of being a participant and the committee member. It has absolutely been an opportunity and immense learning experience. I would like to convey my sincere gratitude to Dr. Manoj Kumar Fukan and Dr. Bijit Chaudhary sir for being the co-convener. I can thank the technical and logistical committee members enough for being the pillars for the workshop. Dr. Sinmar Rajkumar sir, Mr. Sosto Bhattacharya, Mr. Dr. Timakshu Setia, Mr. Prasujya Bhattakur, Mr. Navajyoti Molia, Ms. Anvesha Hazarika, Mr. KVRH Prasad, amongst the others. And finally, I, along with all the other committee members of IVWGST, would like to profoundly acknowledge each and every participant of this workshop. You have sincerely been the heart and soul of the workshop. If you benefited from the lecture series, then I would like to request you to kindly share the video, which would soon be uploaded in the CSIR NIST official channel, YouTube official channel, to share these videos with your friends and colleagues. And with this, I would like to draw the curtains and conclude the final session of IVWGST 2022. Thank you. Good night.
Thank you.